So far, we have seen historical ciphers where we use pen and paper. Then we've seen cipher machines, but now we are living in a digital world. So we work on bits. Now it's a good time to see an example of a modern block cipher and how a brute force attack can be applied to it. So let's start with encoding. Since we are living in a digital world, as I told you, now we are dealing with actually bytes, but all of those bytes are represented by bits. So now we represent characters with bytes or bits, let's say. In the previous example, we worked on letters because we were using the alphabet and punctuation marks and so on. But now in the digital world, we have more than letters or numbers. So we have to agree on an encoding so that the communicating parties can understand each other. So there are some encoding methods. Most famous one is the Ascii table. Most probably you have known, but this table does not contain some Turkish characters or some Latin characters. So for Turkish, we use UTF-8 or sometimes something different. So let's look at the Ascii table. In this table, we represent every character by a byte. So for this reason, this table has 256 different characters. So in other encoding techniques, sometimes you may need to spend 2 bytes to represent the character. So as you can see, the capital letters start from 65. This is the integer representation. In hexadecimal it is here. And it goes like this, some special characters, small letters, and again some characters. And here we have some characters that we see in Turkish, but they're also available in some Latin languages like French. So this is why we have these letters that also appears in Turkish. But we are missing some Turkish characters like Ö. So for this reason, we have to use a different encoding table. Actually, this is still a problem. Some people still keep data written in Turkish in a database table stored as an Ascii table. For this reason, you may still experience something like this when you're trying to find your name in a list. Your name doesn't appear where it should belong because it starts with a Turkish character like Ç. So you go to the bottom of the table and you see yourself there. This is the reason actually, because Ç here comes from later than these letters. This is the whole problem. So for the rest of this course, we assume that all of the communicating parties agreed on an encoding and they can understand each other so that we can transfer bits and we can encrypt the bits so that we can focus on this. So recall that we mentioned that some cryptographic algorithms use keys and some of them don't. For keyless algorithms, hash functions are an example. And for the keyed algorithms, we can divide the crypto into symmetric key cryptography and asymmetric key cryptography. In symmetric key cryptography, we use the same key material for both encryption and decryption. There are some types of algorithms in this category. Block ciphers, stream ciphers, the most famous ones for encryption. But I would prefer to add a third one here, say sponge constructions or permutation-based cryptography, because nowadays many designs are no longer block ciphers or stream ciphers. Instead, they use a very huge internal state and produce the output from there. We will see examples, and I will try to show you how we can implement them, probably focusing on the Ascii cipher. So I no longer actually believe that we can divide symmetric key encryption algorithms by block ciphers and stream ciphers. I believe that there is a third one, which is based on sponge constructions. Finally, we have message authentication codes. This is not an encryption algorithm. This is just a method to provide data authentication, and we will see them in the future again. So we focus on, in this course, block ciphers and stream ciphers and sponge constructions. These are encryption primitives. As I told you, message authentication codes is used for data and data origin authentication. However, we cannot separate all of these concepts because you can build one from the other one. For instance, you can use a block cipher to build a stream cipher, a message authentication code, a keyless hash function, and maybe even a sponge construction. And in the asymmetric key crypto systems, we have different types of algorithms, like key agreement protocols, like Diffie-Hellman key exchange. We also have public key encryption algorithms like RSA or Algama, and we have digital signature algorithms. So your attack actually depends on the algorithm that you are trying to break. So if you look at symmetric key crypto systems, we have the secret key, and by using the secret key, we can perform encryption and decryption. So encryption and decryption key may not be identical, but the idea is that once you know one of them, it is very easy to obtain the other one. In other words, one can be obtained from the other in polynomial time. This would make more sense when we talk about big O notation and algorithm complexity and so on. So block ciphers operate on B-bit blocks of data. Plain text is divided into B-bit blocks. Each block is encrypted by a secret key K to produce B-bit output. Output blocks form the ciphertext. So regardless of your input size, it can be 5 megabytes of a file in your hard drive, it can be 1 gigabyte, it doesn't matter. We divide it into B-bit blocks. Then perform the encryption algorithm on these blocks. So how you combine these blocks actually represents your mode of operation, and there are some mode of operation that are secure and some can be broken. But in our attacks, we would mostly focus on a single block. So we would assume that we captured a lot of ciphertext blocks, and maybe we know some of them, their corresponding plaintext blocks, and we will try to capture some parts of the key by this knowledge. So this course will be about trying to get secret key information from these data that we captured. So if from this definition, we can see a block cipher as a permutation from 2B elements to 2B elements, because if the block size is B bits, this means that you can have 2 to the B different input, which is your input space, and the output space is the same, but which element is mapped to which one actually determined by the encryption algorithm you choose and the key you choose. So once you change the key, the permutation changes. And we want that regardless of which key you choose, all of these permutations look random. Nowadays, the block size is 64 or 128 bits. This corresponds to 8 and 16 bytes. So we are actually encrypting 8 character or 16 character at a time. If we go back to frequency analysis, here you can see why the block cipher idea came from there, because substituting one letter with another could be broken. Doing it by 2 characters or 3 characters, that can still be broken by hand. If you increase the number to 4 or 5, computers can be used to break this system. So this is why we choose block size a little bit large, like 8 characters here, so that it is secure. So if you make it very small, like maybe 4 characters, then capturing a lot of plain text and ciphertext might give you the ability to capture the key or decrypt every ciphertext you capture. So key size is important. Nowadays, for instance, for the AES, we use large key size like 128-bit, 192-bit, and 256-bit. Current technology doesn't allow to break any of these. But if you want to be secure for a very long time, for like military grade security, it is a good idea to use larger key. But for personal use, this key length is good enough. So let's start with this and see how it is broken. This was designed by IBM in 1970s, based on an earlier design by Fpgas called the Cipher, actually Lucifer. So in 1976, NSA tweaked the algorithm by changing its S boxes and its key length, because Lucifer had a key length of 128 bits. NSA actually reduced this to 56, and people at that time claimed that computers are not fast enough to perform such a brute force attack, but it turned out to be this is not the case. So it has a block size of 64 bits, it has 16 rounds, and type is face style. This algorithm is currently known as data encryption algorithm, DEA, instead of DES. This is very important because people still think that DES is a standard and it is secure. Even when you search the web, for instance, like search it like encryption or cryptography, there will be web pages describing how the encryption works by giving examples using DES. And this would mislead people to think that DES is still secure and a standard. And there are still a lot of applications where people are using DES for secure communication, which makes no sense. It can be broken instantly, which I will show you in a minute. It became useless after 1990, so like 30 years ago, but people are still using it. This is the problem in actual cryptography. Cryptographers warn people that people should move on from this algorithm, but it takes a lot of time for the industry to adapt it. So the picture of this looks like this. You have the plain text block. You have left and you divide it into two parts, left and right. So 64 bits is divided into 32 bit, right and left. And in each round, right part goes to become the left of the next round, but right part is also fed into round function, and the output is XORed with the left part to obtain the next round's right part. So this is your round function. Initially, you have initial permutation, but this has no cryptographic importance. This was designed so that the data can be read in a proper order for this chip in hardware. Inverse of this permutation is at the end, but it makes it doesn't increase any security or anything. And the key schedule also based on permutations. You have your 64-bit key, but parity bits of the bytes, most significant bits of the bytes are actually used for parity bits, so they are removed after this permutation. So you end up with 56-bit key. There are some rotations, sometimes 1, sometimes 2-bit rotations, depends on which round you are performing the encryption. And there's a permutation here, takes the 56-bit input and produces 48-bit round key, and it is XORed to the input here. But your input was 32 bits, so you duplicate 16 of those bits to obtain 48 bits. You XOR with your key, then perform substitution and permutation operations. So this round function part is pictured here. So the right 32 bits expanded to 48 bits. It is XORed with your key. Then 8 S boxes are applied. These S boxes take 6-bit input and 4-bit output. And for this reason, the output is now 32 bits. A permutation is applied. These permutations are just changing the places of the bits. So very simple operation. And then you XOR with the left part. So these are the S boxes that NSA tweaked. This is the important part because this is where differential cryptanalysis lies. So they tweaked it in a good way, by the way. The Cipher became more secure. So let's look at it because in the following lectures, we will talk about differential cryptanalysis. So let's see how the history actually works here. So in 1976, NSA tweaked IBM's initial design by changing DES S boxes, but didn't explain to IBM why they made such a change. So since IBM has the initial S boxes and the modified one, they analyzed both of them to see which one is better, and they discovered an attack that breaks their initial design, and they called it T attack. So they shared their discovery with NSA, and NSA asked them not to share this knowledge with public, for they had known this attack type for some time and were using it to listen to other countries. So this was kept secret for a very long time. But in 1990s, Biham and Shamir discovered this technique too, and they called it differential cryptanalysis. And with their papers, this was the first public announcement of the technique. So secret agencies knew it for a very long time. Japanese people claim that they knew it since the Second World War, but it was Biham and Shamir who announced it to the world, actually. So for this reason, when Biham gave a invited speech called how to make a difference, because in the differential cryptanalysis, we are just giving input differences so that to see how it affects the output. He got the IACR fellowship for this he gave this talk, and at the end of his talk he thanked every secrecy agency for not sharing this knowledge until he did, so that he get the credit. So until that part, until the discovery of Wilhelm and Shamir, crypto community didn't know this technique. So main idea in differential cryptanalysis is to find the weakness so that a small change in the input provides an anticipated change in the output with high probability. So this was the weakness of the S-boxes where IBM designed. Small changes in the S-box also provided high probability events at the output difference, and NSA modified the S-boxes so that this is no longer the case. So let's look at another example, which we will be working on a lot in this course. It is the President Cipher. This is an ISO standard for lightweight cryptography. It is a very simple design. Block size is 64 bits, so each line in this picture represents a single bit. At the key addition layer, you XOR it with your 64-bit round key. Then you perform S-box operation. This time the input size is 4-bit and output size is 4-bit. And all of these S-boxes are the same. They're identical, and it is given here. So, for instance, if the input of these 4 bits are 0, this means that in hexadecimal notation, it's still 0. So your input is 0. This means that the output would be C in hexadecimal notation. If you turn it into integer, this would be 12. So if you think that the most significant bit is the leftmost one, this would mean that 1, 1, 0, 0. So this is how the S-box layer works. So this is just a lookup table. And then you have a permutation layer where the places of the bits are changed. So this is a single round. You take the output here, move it to the top, and perform the operation 31 times. And this is an SBN cipher, as you can see. And the key length is either 80 bits or 128 bits, depending on your choice. So as you can see, I first showed you a cipher which has a key length of 56 bits. Now I'm giving you a standard which has 80 bit key. So question is this one also secure? In order to see that, we have to see how the exhaustive search works and how many operations we can perform in a second. So an attacker that captures a single ciphertext can try to decrypt it with every possible key to check if it provides a meaningful plaintext. Or in practice, we can do actually something easier. We capture a plaintext and the corresponding ciphertext. And this is not that hard because sometimes you can guess the beginning of a plaintext. For instance, if this is an email, then you can, an encrypted email message, you can guess the first headers so that you can know the first plaintext block and the corresponding ciphertext block. So in that scenario, you know the plaintext block and the ciphertext block. You encrypt the plaintext block you captured with every possible key and check if it matches with the ciphertext you already captured. Such an attack is called exhaustive search or brute force attack. Exhaustive search is a generic attack. In other words, valid for every cipher. So it doesn't matter if your cipher is strong, good, or how you design it, doesn't matter, because with the k-bit key, you actually generate a key space of 2 to the k keys. So we can try all of them one by one. So we can always perform this attack, regardless of how you define the cipher. So for a key-bit keyed cipher, the attacker is required to perform at most 2 to the k encryptions and decryptions. Thus, security of a block cipher is upper bounded by exhaustive search, in other words, 2 to the k encryptions or decryptions. We will refer this quantity as time complexity, and actually in the following lectures, we will always try to obtain attacks that are, and we will represent them with the time complexity, data complexity, and memory complexity they require. So since we can always break a cipher by performing 2 to the k encryptions, aim of the cryptanalysis is to try to break the cipher or its round reduced version with a time complexity less than 2 to the k encryptions. Otherwise, it wouldn't be better than a generic attack like brute force attack. So let's look at security of DES. Biham and Shamir provided the first theoretical attack, differential cryptanalysis on DES, which requires less time than exhaustive search. But this attack required you to capture 2 to the 47 chosen plaintext and their corresponding ciphertext, which is unrealistic. So this was also one of the surprising things, because Biham and Shamir thought that they could break this in a better way, but they couldn't. This is due to the NSA's involvement, because they modified the S-boxes that were initially designed by IBM. Later on, Matsui provided the first experimental cryptanalysis of this by introducing linear cryptanalysis. I think he used all the computers that he has. He was working at Mitsubishi Electronics at the time. So I think he used all of the computers available there and performed this experiment. So actually, this is amazing, because this experimental cryptanalysis requires a lot of computational power. Today, it is very easy, but in 1994, due to the technology, it was very hard. In 1997, a DES child project was initiated, and that break a message encrypted with DES for the first time in public. This was due to the help of internet. Around 78,000 PCs connected to each other, and they all searched different parts of the key space, and finally they obtained the key. And in 1998, EFF actually designed a machine called DES Cracker. This machine contained close to 2,000 custom chips that can perform exhaustive search attack on DES. And this machine actually captures the key in 56 hours. As you can see, it has become more practical each day. So at the time, it was clear that we should move on and leave DES. So DES is only allowed in 1999 in legacy systems, and people are asked to move on to triple DES, which is actually using DES 3 times consecutively. And at 2002, advanced encryption standard became effective. So at this point on, I don't see any reason to use DES or triple DES, since we have AES. So now the question is, how hard is the exhaustive search? So we said that DES has 56-bit key. So an exhaustive search attack requires 2 to the 56 encryption, which is this number. But if you move on to present with the 80-bit key version, this is the number of keys that are possible. So your key space will be as large as this. If you move on to AES, or present with 128-bit key, this is your key space. For 192, it is this, and for 256, it is this. So as you can see, it increases exponentially. So what can we use to perform exhaustive search attack? The easiest thing you can obtain is CPUs, because almost everybody has a computer or a smartphone that has very fast CPUs. But GPUs are better for exhaustive search, because GPUs come with a lot of cores. So modern GPUs have more than 3,000 cores. And since this is embracing the parallelizable operation, where each core can try a different key, you get a 10 to 100 faster performance than a CPU. We also have FPGAs, which are field programmable gate arrays. You can use those devices to perform an exhaustive search attack, but this actually requires more knowledge, because CPUs and GPUs are easy to obtain, because everybody almost have a desktop or a laptop, and all of these devices come with CPUs and GPUs, and you can just download the code from GitHub and perform these exhaustive search attacks. But for FPGAs, you require more knowledge in the area. But once you have a very good optimization for the FPGAs, if you burn it to the silicon and build a hardware only dedicated for this purpose, then you would obtain ASICs, and this would be way more cost effective than any GPU or FPGA. And this is the reason why Bitcoin miners are using actually ASICs. So this is why you cannot mine Bitcoin by using CPUs. Maybe you can mine a little bit Bitcoin with GPUs, but the price cost, the money you pay for the electricity will be much higher than the Bitcoin you mine. So for short keys, people can build ASICs or use a lot of people in the internet with GPUs get together and perform exhaustive search attacks on these ciphers. So let me show an example here. So here's two desktop computers, sorry, two CPUs, with one of them is a desktop, one of them is a laptop. This is from like 2010, very old devices, but all of them are 4 cores. As you can see, desktop computer, when performing an exhaustive search attack on present 80, has like 2 times more performance than a mobile version. So it will take, using a single CPU, like billions of years to break the present 80. But if you move on to GPUs, you can see that these GPUs are also very old, but this number significantly reduces, because for a CPU you can perform like 31 million encryptions per second, but for a very simple GPU now you can perform like 450 million encryptions per second. So you might say that, okay, this is still huge, but we have a lot faster GPUs and we have millions of gamers on the internet. They can get together and break the cipher in a few days. So in a recent actually work, I showed that by using a single GPU, a modern GPU like RTX 3070, an exhaustive search attack on DES, which requires 2 to the 56 encryptions, takes less than a year for a single GPU. So this means that getting a few more GPUs, like a few more people, you can break this in a few hours by GPUs that you can buy for gaming. And for the case of present, you will require millions of gamers to get together and work a lot, but still it can be done. So this is the reason I never encourage people to use keys shorter than 128 bits. So this is very important, because assume that due to technological advancement, we have very fast CPUs, GPUs, and so on, and we assume that we can use every device in the world and perform an exhaustive search attack on 80-bit present in a single second. So assume that we have that much power. Even if we have that much power, then we can still not break 128 bits block cipher, because performing this many operations in a second means that you can perform actually 2 to the 104 encryptions per year, because a year has almost around 2 to the 24 seconds. So even if we can perform this many operations in a second, breaking this one take millions of years. So this is why increasing the key length is very important, and you shouldn't use anything less than this number. Okay. And final topic, so how many rounds the cipher should have? We have seen that present has 31 rounds and DES has 16 rounds. So the thing is that we don't have a direct answer for this, but the common belief is that increasing the number of rounds increases the security, because it will be harder for cryptanalysts to find a weakness and break the cipher. But increasing the number of rounds also reduces the performance. So you should find the optimum place that will give you best security and best performance. A common practice is as follows: designers apply every known cryptanalysis techniques, and if they can break n rounds, most of the time they choose the number of rounds as greater or equal to 2n to stay on the safe side. Because once they break n rounds, some people will find more weakness and break n+1 round, n+2 round, because attacks always gets better and better. And day by day, we discover new cryptanalysis techniques, and we reduce the maybe the time complexity of the attacks that we have previously done, and we can attack more rounds. So for this reason, designers generally try to be on the safe side. So in this course, we will try to see how many rounds of a cipher we can break to determine its security. If we can break the total number of rounds, so the full cipher, then we will say that this cipher is broken and we cannot trust a cipher that is broken.